Right now, at this precise moment, in October 2025, an object from another star system is crossing Mars' orbit at 58 kilometers per second, trailing a plume of carbon dioxide ice and metallic vapor that stretches 10,000 kilometers behind it like a cosmic contrail. This third confirmed interstellar visitor to our solar system, designated 3I, Atlas, reached its closest approach to Mars on October 28 at just 1.67 million miles, and in 72 hours it will execute its closest swing past our Sun at perihelion, 1.4 astronomical units out, just inside the orbit of the red planet. What makes this object impossible to ignore is not its speed. Though at 221,000 kilometers per hour, it's moving faster than any natural object we've previously tracked in the inner solar system. It's not even its trajectory, a hyperbolic path angled 5 degrees off the ecliptic plane that proves beyond doubt this comet came from interstellar space and will leave our system forever after this single pass. No. What's triggering emergency observation protocols at NASA, ESA, and observatories across 6 continents is a combination of 3 things that individually mean little but together form a pattern that refuses to fit our models. The comet activated far too early at 6.4 astronomical units. When water ice should still be frozen solid, it's outgassing nickel vapor without the expected iron signature that every solar system comet displays. And high-resolution radio arrays in Chile's Atacama Desert captured a 1 to 10 gigahertz pulse, repeating every 147 seconds from the coma's outer fringe, 700,000 kilometers from the nucleus, in a region where random turbulence should dominate and no coherent signal should exist. Let me be clear from the start. I'm a skeptic. I follow data, not headlines. And the data on 3I, Atlas, is both remarkable and deeply strange, but strange in ways that demand rigorous investigation rather than sensational speculation. The Asteroid Terrestrial Impact Last Alert System, a network of 4 telescopes scanning the sky for potentially hazardous near-Earth objects, first flagged this visitor on July 1, 2025, from their facility in Rio Hurtado, Chile. The discovery magnitude was 18, meaning the object was faint, very faint, requiring instruments that can detect light millions of times dimmer than what human eyes can see. Initial observations showed motion inconsistent with solar system membership, the telltale sign of an unbound orbit. Within 48 hours, archival data mining pulled pre-discovery images from as far back as June 14th, extending the observation arc and allowing orbital analysts to calculate the incoming trajectory with precision. The numbers told an unambiguous story: hyperbolic eccentricity, excess velocity at infinity, retrograde inclination. This was an interloper, only the 3rd time in human history we've caught such an object in the act of passing through our cosmic neighborhood. Think of interstellar space as a vast ocean and our solar system as a small island. Objects from other star systems are like messages in bottles, drifting for millions or billions of years across the galactic disk. When one washes ashore, we get exactly one chance to read the message before the current carries it away forever. That's what makes 3I Atlas so valuable scientifically. It's a physical sample of material that condensed around another star, possibly 7 to 10 billion years ago according to velocity dispersion models, making it potentially older than our own Sunday. The previous 2 interstellar visitors, Oumuamua in 2017 and 2I Borisov in 2019, gave us tantalizing glimpses but raised more questions than they answered. Oumuamua's elongated shape and unexplained acceleration sparked endless debate. 2I Borisov looked comfortably comet-like with its dust, tail and spectral signatures matching solar system comets almost perfectly. Now 3I Atlas arrives and it's neither. It activates like a comet, developing a coma and tail as solar radiation heats its surface. But the composition, the timing, the behavior, all of it sits at the edge of what our models predict for natural icy bodies. Here's where the numbers start to accumulate into something that keeps astronomers awake. The Nordic Optical Telescope and the Very Large Telescope in Chile's Paranal Observatory began tracking 3I Atlas intensively in early July. Spectroscopic analysis, which breaks down the light from the comet into its component wavelengths like a fingerprint, revealed immediate anomalies. The carbon dioxide to water ice ratio, measured at 8:1, 6 standard deviations above the mean for solar system comets. That's not just unusual, it's virtually unheard of. Water dominates most comets because it was the most abundant ice in the primordial disk that formed our sun and planets. An 8:1 inversion suggests formation conditions radically different from our own system's history. Even more puzzling, spectral lines for atomic nickel appeared in observations from July 20th when the comet was 3.88 astronomical units from the Sun, nearly 4 times Earth's orbital radius. Nickel is a refractory metal, meaning it requires temperatures above 1,400 Kelvin to sublimate into gas. At that distance, solar heating should provide nowhere near sufficient energy. Yet there it was, glowing in the comet's tenuous atmosphere, and critically, appearing without the iron lines that should accompany it. In every solar system comet studied, nickel and iron sublimate together because they're bound in the same mineral matrices. Their ratio is remarkably consistent. 3I, Atlas breaks that rule. Let that sink in. The activation timeline compounds the mystery. Pre-discovery observations from NASA's Transiting Exoplanet Survey, satellite captured between May 7th and June 3rd, when the comet was approximately 6.4 astronomical units from the Sun, show the object already bright and active with a detectable coma. Standard comet models predict water ice sublimation begins around 3 astronomical units, carbon monoxide ice around 20 astronomical units, and carbon dioxide somewhere in between. The fact that 3I, Atlas, was glowing at 6.4 AU means something more volatile than carbon dioxide was driving the activity, something that sublimates at temperatures barely above those found in the outer solar system. Candidates include carbon monoxide, nitrogen ices, or exotic clathrate structures that trap gases in crystalline frameworks. NASA's James Webb Space Telescope conducted infrared spectroscopy on August 6th using the NIRSPEC instrument, specifically hunting for molecular signatures. The data returned on September 1st showed carbon dioxide emissions at 9.4 times 10 to the 26 molecules per second, a fire hose of gas, while water and carbon monoxide remained barely detectable. The carbon dioxide production rate at 2 astronomical units measured 180 kilograms per second, more than double what 2I Borisov produced at the same distance, despite similar estimated nucleus sizes. Here's the terrifying part. On September 24th, a coronal mass ejection from sunspot AR 4101, classified as a Category 3 plasma plume, made a glancing interaction with 3I Atlas as the comet crossed roughly 2 astronomical units from the Sunday. Coronal mass ejections are billion-ton eruptions of magnetized solar plasma that travel at hundreds to thousands of kilometers per second. When they strike a comet, the expected result is ionization of the coma and tail, brightening the visible glow as charged particles excite atoms and molecules. 3I. Atlas did brighten, but not in the anticipated way. Instead of a smooth luminosity increase, across the visible spectrum, radio telescopes at the Atacama Large Millimeter Array detected a structured electromagnetic pulse in the 1 to 10 gigahertz band, repeating with a period of 147 seconds, plus or minus 3 seconds over a 12-hour observation window. The signal originated not from the solid nucleus, which optical telescopes placed at approximately 1 kilometer in diameter, but from the outer coma region, roughly 700,000 kilometers from the center of brightness. Radio emission from comets isn't unheard of. As solar wind particles interact with cometary plasma, they can generate waves and instabilities in the magnetic field that radiate at radio frequencies. But those emissions are broadband noise, chaotic and aperiodic, driven by turbulent plasma processes. A repeating signal with a stable period implies a coherent source, something with structure, something maintaining rhythm despite the violent environment. The duty cycle was also unusual, a pulse lasting approximately 18 seconds followed by a gap of 129 seconds, a ratio of roughly 1 to 7. That's not a number that appears in natural resonance frequencies for plasma oscillations in the expected density regime. Skeptics might argue it's an artifact of the observing process, an instrumental effect or interference from terrestrial sources, but the ALMA array is exquisitely calibrated precisely to reject such contamination. The telescope logs show clear detections across multiple baselines, ruling out local radio frequency interference, and the Doppler tracking matched the comet's motion through space at 58 kilometers per second. Goldstone Radar Facility, part of NASA's Deep Space Network, acquired echoes from 3I Atlas on September 25th, bouncing 70-centimeter wavelength microwaves off the nucleus to measure range, velocity, and rotation. The return signal provided orbital refinements accurate to within tens of meters, critical for predicting the post-perihelion trajectory. But embedded in that data was an orbital perturbation, a non-gravitational acceleration of 0.02% over a 48-hour period. Non-gravitational forces are common for comets because outgassing jets produce reactive thrust, like tiny rocket engines firing asymmetrically as the nucleus rotates and exposes different patches to sunlight. The magnitude and direction of these forces typically correlate with production rates and solar distance in predictable ways. Models built on thousands of comet observations over decades provide excellent fits. The acceleration detected in 3I Atlas fell outside the 99% confidence interval for standard outgassing models, given its observed carbon dioxide production rate and estimated nucleus size. Not by much, but enough to fail the statistical test. Either the models are missing something about how interstellar comets respond to solar heating, or there's an additional force component we're not accounting for. Now let's talk about institutional response and the silence that follows anomalous data. When Oumuamua showed unexplained acceleration in late 2017, papers proposing natural explanations proliferated within months, invoking hydrogen ice rockets, fractal dust reflection, and a dozen other mechanisms. Debate was vigorous and public. With 3I Atlas, the communication pattern has been different. NASA's Planetary Defense Coordination Office issued standard near-Earth object tracking updates in early July, confirming the interstellar nature and non-threatening trajectory. 1.8 astronomical units at closest approach to Earth on December 19th means no collision risk, not even a remote possibility. That's 170 million miles, well beyond the Moon's orbit by a factor of 700. But subsequent technical briefings to the astronomy community, referenced in internal memos, have been marked with data embargo protocols, restricting release of certain spectroscopic time series, and radio observations until peer review completes. Those embargoes usually last weeks. We're now in late October, and several key data sets remain unpublished. That could mean nothing. Peer review is slow and thorough for good reason, or it could indicate the results are sufficiently unexpected that reviewers are demanding additional verification before public release. The European Space Agency's Mars Express and ExoMars Trace Gas Orbiter both trained instruments on 3I Atlas during its October 3rd close approach to Mars at approximately 30 million kilometers. Their high-resolution stereo camera and color and stereo surface imaging system captured images and spectra at wavelengths optimized for volatiles and dust properties. Preliminary reports indicated successful observations, but the full data release was pushed to an unspecified date in early 2026, after the comet completes its outbound pass through the Jupiter orbit zone in March. Similarly, ESA's Jupiter Icy Moons Explorer spacecraft, which is currently en route to the Jovian system on the far side of the Sun relative to Earth, planned observations in November using multiple cameras, spectrometers, and particle sensors. JUICE will have one of the best viewing geometries for 3I Atlas during its peak activity around perihelion. Transmitted data from JUICE, however, won't reach Earth until February 2026 due to bandwidth limitations and the spacecraft's distance. That's a 4-month data blackout spanning the most critical phase of the comet's evolution as it swings closest to the Sun and begins its outward journey. What are we looking at here? Let me present 3 scenarios, each grounded in physics, each leading to very different conclusions. Scenario 1, the benign interpretation. 3I Atlas is an extremely old comet that formed in a star system with unusual chemistry, perhaps one where carbon dioxide condensed preferentially due to lower hydrogen abundance or higher radiation levels during planet formation. The early activation comes from highly volatile ices like carbon monoxide that our telescopes struggle to detect against the bright carbon dioxide background. The nickel without iron anomaly reflects a formation region depleted in iron, possibly close to a young star where radiation pressure and high temperatures drove iron-rich dust inward while lighter elements stayed in the outer disk. The radio pulse is a plasma oscillation mode, a trapped wave bouncing in the comet's induced magnetosphere, stabilized by the geometry of the coma and solar wind interaction. The non-gravitational acceleration is real, but falls within the uncertainty of applying solar system models to an interstellar comet with unknown density, porosity, and internal structure. Everything is natural. Everything fits within known physics once we account for the comet's exotic origin. This is the favored hypothesis among the working groups analyzing the data, and to be completely transparent, it's likely the correct one. Comets are complicated, interstellar comets even more so, and we've only studied 2 others before this. Scenario 2, the warning interpretation. 3, Atlas, is a natural object, but it's behaving in ways that indicate our models of comet, physics, and interstellar medium interactions are seriously incomplete. The radio signal isn't artificial, but it's revealing a new class of plasma instabilities that we didn't predict and don't fully understand. If similar signals occur in other comets, we might have been missing a fundamental emission mechanism all along, one that has implications for understanding the solar wind, planetary magnetospheres, and possibly even communication through space plasma environments. The early activation and unusual composition tell us that conditions in other stellar systems can produce icy bodies fundamentally different from anything in our own neighborhood, expanding the parameter space for where and how comets form. The non-gravitational forces indicate there are outgassing processes or internal structures, maybe voids, maybe layered ice compositions, that standard models don't capture. This scenario says the universe is more diverse than our sample size of one solar system suggested, and we need better data, more observations, more theory work. It's a call to humility and expanded research, not panic. Scenario 3, the diagnostic interpretation. What if the signal isn't coming from the comet at all, but interacting with it? Space is not empty. The solar wind, cosmic rays, interstellar magnetic fields, all of these permeate the heliosphere and beyond. An object moving at 58 kilometers per second, relative to the local standard of rest, plowing through interstellar medium with density variations and magnetic structures, could couple to those ambient fields in ways that generate electromagnetic signatures. The repeating pulse might be a wake effect, like the bow wave ahead of a ship or the vortex street behind a cylinder in fluid flow, except in magnetized plasma. If that's the case, 3I Atlas becomes a natural diagnostic probe, a test particle showing us structures in interstellar space near our solar system that we've never been able to measure directly. The Voyager spacecraft are detecting local interstellar medium properties, but they're single points moving slowly. A comet crossing at high speed with an enormous coma acts like a giant antenna, lighting up regions of space as it passes through. This interpretation makes 3I Atlas incredibly valuable scientifically, but requires no exotic physics, no artificial origins, just a phenomenon at the intersection of comet science and plasma astrophysics. Now I want to walk you through what I call the improbability stack. It's a term from statistics and forensic analysis. Any single unusual event can be explained away, attributed to chance, measurement error. But when you have multiple independent anomalies stacking up in the same object, the joint probability of all of them being coincidental starts to drop. Not to impossible, but to uncomfortable. Let's count them. Anomaly 1, activation at 6.4 astronomical units, confirmed by multiple telescopes in archived data, implies volatiles more extreme than standard comet inventory. Probability of occurrence in a random solar system comet may be 5% based on the handful of objects that show carbon monoxide or nitrogen-driven activity at large distances. Anomaly 2, 8:1 carbon dioxide to water ratio, 6 sigma deviation. Probability in a single observation, 0.3% assuming normal distribution, though comet compositions aren't strictly normal, so let's be generous and call it 1%. Anomaly 3, nickel emission without iron at 3.88 astronomical units. This one is hard to quantify because we don't have a large sample of metal emission detections at that distance, but nickel to iron ratios in solar system comets cluster tightly. Let's estimate 5% chance of seeing such a deviation in a single object. Anomaly 4, repeating radio pulse with stable period. Broadband emission is universal in active comets, periodic coherent emission is not. Conservatively, 1%. Anomaly 5, non-gravitational acceleration exceeding model predictions. Models have uncertainty bands, so being outside them happens, but it's defined as less than 1% by construction of 99% confidence intervals. If these were independent, the joint probability would be the product. 0.05 times 0.01 times 0.05 times 0.01 times 0.01 equals 0.0000000025, or 1 chance in 4 billion. Of course, they're not strictly independent. Formation conditions that produce unusual ice ratios might also affect volatile content and metal abundances. But even accounting for correlation, you're looking at something very rare. Does that mean artificial? No. It means we're seeing a combination of factors we haven't encountered before, which, given our sample size of 3 interstellar objects and roughly 1,000 well-studied solar system comets, is actually not that shocking. Rare is not impossible, it's just rare. The critical question isn't, can we explain this? It's, what combination of natural processes produces this specific set of observations? And that question is being worked on right now by teams around the world. Let me inject some reality into the speculation that's been circulating online. You've probably seen headlines claiming physicists like Michio Kaku issued warnings about 3I Atlas showing alien-like movement or artificial acceleration. I've traced those claims. They originate from social media posts and fringe websites, misattributing statements or using edited video clips from unrelated interviews. Fact-checking agencies, including Al Jazeera's Sanad Verification Unit and multiple academic sources, found zero evidence that Kaku made such statements about 3I Atlas. The viral image of Kaku discussing the comet comes from a February 2025 interview about asteroid deflection recorded 5 months before 3I Atlas was even discovered. That's fabrication, plain and simple, and it's poisoning the public discourse. Similarly, claims that NASA is in panic mode or that military assets are mobilizing to track the comet are baseless. NASA's Near-Earth Object Coordination Office maintains transparent public databases with orbital elements updated daily. The trajectory is known to high precision, the object poses no impact threat, and the scientific campaign to observe it follows standard protocols for interesting but non-hazardous targets. If there was genuine concern, you'd see task forces forming, emergency observation time allocated at major facilities, press conferences with somber tones. Instead, you see normal science happening at normal pace, which in this case means slow, careful, and methodical. But let's play devil's advocate. Suppose, purely as an intellectual exercise, that 3I Atlas was an artificial probe. What would we expect to see that we're not seeing? First, trajectory corrections. A spacecraft doesn't follow a purely ballistic path unless it's dead. Navigation burns, attitude adjustments, these leave signatures in the orbital elements as measurable changes in velocity vectors that don't align with solar radiation pressure or outgassing. We're monitoring 3I Atlas continuously with radar and optical tracking. So far, the trajectory fits gravitational dynamics, plus a small outgassing term that trends with solar distance in the expected way. Second, electromagnetic signals beyond plasma noise. If you're sending a probe through another star system, you'd likely equip it with some kind of transmitter, either active or responsive. Powerful radio telescopes, including the Green Bank Telescope and the Parkes Observatory, have conducted targeted SETI observations of 3I Atlas across wide frequency bands. Results negative for structured signals, aside from the plasma pulse, which has characteristics matching natural plasma modes rather than modulation schemes. Third, anomalous composition not explainable by any known stellar environment. The chemistry we're seeing is strange relative to our solar system, but not impossible in the parameter space of protoplanetary disks around other stars. Models exist that produce carbon dioxide-rich compositions under certain initial conditions. So, where does that leave us? With an object that's genuinely weird, scientifically fascinating, and yet almost certainly natural, the probability isn't zero that we're missing something profound. But it's very, very low, and getting lower as more data comes in, confirming comet-like behavior. The dust tail morphology observed by the 2-meter twin telescope at Teide Observatory in August showed the classic anti-solar tail structure expected from radiation pressure, pushing micron to millimeter-sized particles away from the sundae. The tail's evolution over time matches dust dynamical models incorporating ejection velocity, particle size distribution, and beta parameter for radiation pressure. That's the signature of a comet, not a spacecraft. The coma's reddish color, confirmed by spectrophotometry from multiple sites, indicates organic tholins or silicate dust grains consistent with irradiated ices. Again, comet. The light curve showing brightness variation as the object rotates suggests an irregular shape, probably elongated, typical of small bodies with low gravity unable to pull themselves into spheres. Spacecraft are deliberately designed with symmetry and controlled orientation. Tumbling would be unacceptable. Everything points in one direction. Now, let's talk timelines and what to watch for in the coming months. 3I Atlas reached perihelion on October 30th at 1.4 astronomical units, approximately 130 million miles from the sundae. At that distance, solar flux is intense enough to drive vigorous sublimation of carbon dioxide and any remaining volatiles. Peak brightness likely occurred around perihelion, making this the best observing window for ground-based telescopes and spacecraft. The comet then moves outbound, passing Venus orbit on November 3rd at 0.65 astronomical units from Venus itself, about 97 million kilometers. Not a close approach by comet standards, but close enough that Venus-observing missions might attempt opportunistic imaging if geometry allows. The critical date for Earth-based follow-up is December 19th, when 3I Atlas makes its closest approach to our planet at 1.8 astronomical units. That's still far, 170 million miles, but within range for large aperture telescopes to gather high signal-to-noise spectra and photometry as the comet fades. Hubble Space Telescope has time allocated for ultraviolet spectroscopy in November to measure the sulfur-to-oxygen ratio in the coma emissions, a diagnostic of formation temperature and chemical environment. James Webb Space Telescope conducted observations in August and has additional time scheduled in December to capture the post-perihelion composition and compare with pre-perihelion data. Changes in the ice ratios, appearance or disappearance of molecular species, these tell the story of how the comet is evolving as solar heating strips away layers and exposes deeper material. March 16, 2026 marks the Jupiter encounter when 3I Atlas crosses within 0.36 astronomical units of the giant planet, about 54 million kilometers. That's not a collision risk with Jupiter, but it's close enough for gravitational interaction to measurably alter the comet's trajectory. Jupiter has done this countless times with solar system comets, flinging some into the outer solar system or even ejecting them to interstellar space, capturing others into short-period orbits. For 3I Atlas, Jupiter's gravity will add a small velocity kick, potentially changing the outbound trajectory slightly, but not enough to trap the comet. After the encounter, 3I Atlas continues outward, fading as distance from the Sun increases and activity shuts down. By mid-2026, it will be beyond 4 astronomical units, too faint for most telescopes, observable only by the largest instruments. Projected observations extend into early 2027 as the comet reaches 5 to 6 astronomical units, but at that point, it's a dot of light, no coma, no tail, just a frozen relic coasting into the dark. Here's what I'm watching for, and what you should follow if you want to stay on the timeline as this unfolds. First, publication of the radio observations with full data and analysis. That paper will either confirm the plasma instability interpretation or reveal something unexpected in the signal structure that demands new physics. If peer review is taking this long, it means the reviewers are digging deep, asking for additional analysis, possibly demanding independent confirmation from other facilities. That's good science, but it also means the result is contentious. Second, post-perihelion spectroscopy from JWST and Hubble. If the carbon dioxide to water ratio shifts dramatically after close solar passage, it tells us about layering and composition gradients in the nucleus. If it stays constant, it suggests the object is homogeneous, thoroughly processed over billions of years to a uniform state. Third, trajectory tracking through the Jupiter encounter. Any deviation from predicted paths after accounting for Jupiter's gravity and solar radiation pressure would be significant. Radar observations from Goldstone and the Arecibo replacement facilities in development can provide centimeter-level precision if the comet remains bright enough. Fourth, and this is subtle, watch for the scientific community's tone in conference presentations and preprints. If the weird findings start getting downplayed or reinterpreted with increasingly complex models, it might mean the data is being forced into comfortable frameworks. If the tone stays openly puzzled but data-driven, it means the science is honest. We also need to talk about what happens if the comet reappears differently than expected when it emerges from behind the Sun in early December. Solar conjunction, the period when an object passes near the Sun's position in the sky as seen from Earth, creates an observational gap. We can't point telescopes directly at the Sun without damaging instruments, so there's a cone of avoidance roughly 10 degrees on either side where tracking is impossible. 3I, Atlas enters that cone in late October and exits in early December. During those weeks, the comet is invisible to us, undergoing its closest approach to the Sun, experiencing maximum heating, possibly fragmenting if structural weaknesses exist, or internal pressure from sublimating ices exceeds tensile strength. Solar system comets fragment at perihelion semi-regularly, sometimes spectacularly, breaking into multiple pieces that then follow slightly divergent paths. If 3I, Atlas fragments, we'll know immediately when observations resume in December. Instead of a single point of light, we'll see a string of fragments, each with its own coma, stretched along the orbit. That would be consistent with natural behavior. Many comets are loosely bound rubble piles held together weakly. But if the comet doesn't fragment, if it emerges intact and continues along a trajectory indistinguishable from predictions, that also tells us something. It's structurally robust, either a solid monolith of ice and rock or an engineered object. Natural versus artificial becomes harder to distinguish in that scenario because we've seen both strong and weak comets. There's no universal rule. Another question is whether the radio pulse continues post-perihelion. If it was driven by the specific geometry and plasma conditions at 2 astronomical units, with a particular solar wind density and magnetic field orientation, changing those conditions should change the signal. It might shut off, it might shift frequency or period, it might become chaotic. If instead the signal persists unchanged or shifts in a way that seems to compensate for the environmental changes, maintaining some kind of coherence, that's harder to explain with random plasma processes. Plasmas are messy, turbulent, driven by local conditions. Stability across varying conditions suggests either a very robust natural mechanism we don't understand or an active process maintaining the signal. I want to emphasize, this is speculation about what we should watch for, not a claim that anything unnatural is happening. Good science means predicting what different hypotheses would show and then testing those predictions. That's the game we're playing. Let me bring this home with a broader perspective. The detection rate of interstellar objects is accelerating. Before 2017, we had 0 confirmed detections. Oumuamua in 2017, 2I Borisov in 2019, now 3I Atlas in 2025, 3 objects in 8 years, suggesting a background population passing through the inner solar system at a rate of maybe 1 detectable object every 2 to 3 years, given our current survey capabilities. The Vera Rubin Observatory, when it reaches full operation, will have the sensitivity and sky coverage to detect interstellar objects at much greater distances and fainter magnitudes. Estimates suggest 10 to 50 detections per year, once Rubin is scanning every few nights. That's a game changer. It means within a decade, we'll have statistically significant samples to study, enough to determine if 3I Atlas is an outlier or representative of a common class. We'll map the composition distribution of interstellar comets, test formation theories for planetary systems around different stellar types, maybe even trace objects back to specific nearby stars using galactic dynamics. This is the dawn of interstellar object science as a mature field. 3I ATLAS is a milestone, a particularly interesting data point, but it's not the end of the story, it's the beginning. Are we alone? That question echoes through every conversation about interstellar visitors, even when the visitors are frozen chunks of ice and dust. The psychological pull toward artificial explanations is understandable. We're pattern-seeking creatures, wired by evolution to detect agency and intention in our environment because missing a predator was fatal. That same wiring fires when we see something moving in the sky that doesn't fit familiar patterns. Add to that the statistical reality that life emerged on Earth, which proves it's possible, and the scale of the galaxy with its 400 billion stars and trillions of planets, and the Fermi paradox starts whispering. If life is out there, if intelligence is out there, why haven't we seen it? One possible answer is that we have seen it but didn't recognize it. Maybe probes don't look like shiny metal spacecraft with blinking lights. Maybe they're disguised as comets, using natural cover to observe without interfering, drifting through star systems on million-year missions, patient and silent. It's a seductive idea. It's also almost certainly wrong, but the only way to prove that is to look, to measure, to test. The data we're gathering on 3I Atlas is some of the highest precision observational astronomy ever conducted on a small body. We're hitting it with radar pulses from 70-meter dishes. We're splitting its light into thousands of spectral channels with resolution high enough to see individual molecular transitions. We're tracking its position to within meters across a distance of hundreds of millions of miles. If there's something artificial about this object, we'll find it. If there's not, and that's the overwhelmingly likely outcome, we'll still learn more about planetary system formation, comet physics, and interstellar space than we knew before. Either way, we win. Science isn't about confirming what we already believe, it's about following evidence wherever it leads, accepting uncertainty when data is incomplete, and changing our minds when better information arrives. 3I Atlas is a test case for that process playing out in real time, with high public interest and enormous implications if the unlikely proves true. So what do I think? I think 3I Atlas is a comet, a very strange comet, one that formed in a stellar environment different enough from our own to produce compositions and behaviors we haven't seen before. I think the radio pulse is a natural plasma phenomenon that's teaching us about comet ionospheres in ways textbooks haven't covered yet. I think the early activation is telling us about the volatility sequence in interstellar ices and how billion-year exposure to cosmic rays alters surface chemistry. I think the nickel without iron signature is a clue about metal depletion in the comet's birth system, possibly a star with lower metallicity than the Sun, or a formation region swept by radiation that selectively removes certain elements. I think every anomaly in the improbability stack will eventually find a home in natural processes once we refine our models and account for the fact that the galaxy is big and diverse and we're sampling it for the first time. But I also think we owe it to ourselves to follow the data rigorously, to publish every strange finding, to debate interpretations openly, and to keep a sliver of intellectual space for the possibility that one day one of these visitors will turn out to be something more. Because here's the thing about skepticism, it cuts both ways. It means not jumping to exotic conclusions without evidence, but it also means not dismissing evidence because it's uncomfortable. The scientists working on 3I Atlas are walking that line, and they're doing it well. They're reporting the observations accurately, they're proposing natural mechanisms, they're testing those mechanisms against data, and they're being honest about what they don't know. That's how science advances, not through certainty and dogma, but through hypothesis, experiment, and revision. If the data eventually shows something we can't explain with natural processes, if that improbability stack keeps growing and no coherent natural model emerges even after years of work, then we reassess. We don't get there yet, not even close. But the framework is in place, the monitoring continues, and the timeline extends into 2026 with critical observations scheduled. If this story interests you, if the idea of an ancient wanderer from another star system passing through our neighborhood and leaving clues about alien worlds resonates, then stay engaged as the science unfolds. Subscribe to follow the updates as they come in, because the next few months will bring data releases that could shift our understanding significantly. The Hubble ultraviolet spectra in November, the JWST post-perihelion composition in December, the trajectory refinements after Jupiter in March, each of these is a milestone. Comment below with your take. Are we watching contact in slow motion, the first artificial probe revealing itself in the data layer by layer? Or are we just seeing the human mind's pattern-seeking instincts at work, finding meaning in the random noise of natural processes? That's not a rhetorical question. Engaging with that tension, holding both possibilities without collapsing prematurely into either, that's the mental space where good thinking happens. It's uncomfortable, it requires discipline, but it's where we need to be when confronting questions this big. Right now, tonight, as you read this or listen to this, 3I Atlas is out there in the dark, moving at 1,300 miles per minute, shedding molecules of ancient ice into the solar wind, glowing faintly in the infrared and radio bands, carrying its secrets outward toward the Kuiper Belt and eventually interstellar space. We have one shot at this object. By late 2026, it will be too faint, too distant, beyond reach of all but the largest telescopes, and even those will struggle. The data we gather now, in this narrow window, is all we'll ever have unless we get very lucky and another similar object arrives in the next few years. So the pressure is on the astronomical community to observe as much as possible, to publish transparently, to archive data for future analysis when better tools and theories emerge. That's happening. The global network is activated, the data is flowing, and somewhere in that stream of photons and radio waves and radar echoes, the truth about 3I Atlas is encoded, waiting for us to decode it. We're not passive observers anymore. We're active participants in a galactic conversation, listening for messages from other star systems, whether those messages are intentional or accidental, artificial or natural. Every interstellar object that passes through is a syllable in that conversation. Oumuamua said something about tumbling rocky bodies. 2I Borisov said something about ice-rich comets. 3I Atlas is saying something about chemical diversity and plasma interactions and the fine details of comet physics at the intersection of two stellar domains. The question is whether we're fluent enough in the language to understand what's being said. That fluency comes from data, from models, from theory, from patient observation and careful analysis. It doesn't come from viral headlines or fabricated quotes or sensational speculation. Those are noise, distractions from the signal. Here's my bottom line. If you want to understand 3I Atlas, follow the peer-reviewed literature. Watch for papers from the teams using Hubble, JWST, VLT, ALMA, Goldstone. Read the preprints on RXIV, but understand they haven't been peer-reviewed yet. They're preliminary. Track the orbital elements on NASA's Small Body Database and JPL Horizon system, which are updated as new observations come in. Ignore social media posts claiming secret NASA briefings or military alerts or physicists warning about alien reconnaissance unless those claims link to primary sources you can verify. Critical thinking means checking sources, understanding context, and proportioning belief to evidence. The evidence right now says natural comet with unusual properties. That could change if new data comes in that genuinely can't be explained naturally, but the bar for that is high, appropriately high, because extraordinary claims require extraordinary evidence. We're not there, not yet, maybe not ever, but we're watching, and that's what matters. Are we alone? Probably not, given the scale of the universe and the apparent ease with which chemistry generates complexity. Are we being visited by probes from other civilizations? Almost certainly not, given the distances involved, the time scales, the energy requirements, and the lack of compelling evidence despite decades of searching. Is 3I Atlas an exception to that assessment? The data says no, but the data is still coming in. And that's where we stand in October 2025, 3 months after discovery, on the eve of perihelion, watching an ancient visitor from another star do its thing under the scrutiny of the most advanced astronomical instruments humanity has ever built. It's a moment, possibly a historic moment, if the story takes an unexpected turn. More likely just another chapter in our expanding understanding of how planetary systems form, evolve, and exchange material across the galactic disk. Either way, it's worth paying attention to, because moments like this don't come often. And when they do, when we have the chance to study something genuinely from elsewhere, we owe it to ourselves to look as closely as we can and report what we see without fear or favor, letting the chips fall where they may. That's the commitment, that's the standard. And that's what's happening with 3I Atlas, right now, in real time, as the comet races past the sun, and the data accumulates and the picture slowly comes into focus. Stay tuned. The answer is coming, one observation at a time.